Now let's talk about the history of the periodic table. The periodic table was originally constructed to represent the patterns observed in the chemical properties of the elements. This was a very empirical version of the periodic table. It was, let's see what we've got, let's write down some masses, let's write down some properties, let's write down some densities, and see if we can start to make sense of these things. Dalton actually started some of that when he started to list some of the elements based on the atomic mass. But it was Mendeleev's periodic table where he kind of noticed some of these trends and not just sorting them by mass. So it emphasized how the table could help estimate and predict the existence and properties of, at the time, unknown elements. And it rectified several values of the atomic masses. So Dalton had some a little bit wrong. Mendeleev fixed some of that, and he's like, okay, I'm starting to see some trends. The current periodic table lists elements by their atomic number rather than their atomic mass. And as we'll see, it's actually organized based on the electronic structure and the quantum numbers we just talked about. But there were 114 elements known by 1999. The majority of the elements were discovered between 1735 and 1843. How do we organize 114 different elements in a meaningful way that will allow us to make predictions about undiscovered elements? Can we arrange the elements to reflect trends in chemical and physical properties? The first attempt, Mendeleev and Mayer, arranged the elements in order of increasing atomic weight, and the modern periodic table arranges them in increasing atomic numbers, because we know that the weight's going to vary based on isotopes, whereas what makes one element different from another element is actually the atomic number. Right, so 1864, John Newland's law of octaves said that every eighth element kind of had similar properties when arranged by atomic masses, and that doesn't really work past California. 1869, Mendeleev and Lothar Meyer independently proposed the idea of periodicity, or a recurrence of properties. So here's Mendeleev. He grouped elements, the 66 that were known, according to their properties. And what was cool is that he was able to predict properties for elements that weren't discovered. So he had he predicted this element called ecosilicon, right? So something below silicon. And he said, well, ecosilicon, we're going to say it's got an atomic mass of about 72, right? And we now know that the element below silicon is germanium. And it's got 72.59, and predicted its density to be about 5.5. That's 5.35. Predicted a high melting point. Its melting point is 349. It said it should be gray. It's gray. It's a refractory oxide. It's refractory oxide. Oxide density is 4.7. He said, oh, it's 4.7. And so really good at guessing what the properties are based on looking at some of those trends, right? In an attempt to have the chemical conception of the ether, he put forward a hypothesis that there existed two inert chemical elements of lesser atomic weight than hydrogen. Of these two proposed elements, he thought the lighter to be an all-penetrating, all-pervasive gas, and the slightly heavier one to be a proposed element, coronium. So this is actually the sketch of his initial periodic table. The four predicted elements lighter than the rare earth elements, eka-boron, eka-aluminum, eka-manganese, and eka-silicon, proved to be good predictors for scandium, gallium, technetium, and germanium, respectively. Technetium is cool stuff. They use that in radiological imaging. It's an unstable isotope and is man-made. And this is a what did we know when version of the periodic table. So ancient times, right, we knew things like copper and silver and gold and iron. Right, in the Middle Ages, you got phosphorus. There's a really famous painting of an alchemist discovering phosphorus, arsenic, antimony, bismuth, zinc, platinum. In the Age of Enlightenment, right, we start to get a big burst of all of these other guys in here, right, our noble gases, oxygen. It's not until like the 1800s that we start to get some of the noble gases, and then these pink guys, these are coming post-nuclear age, right? Technetium, hafnium. A lot of these are radioactive elements. Although it was a good model, Mendeleev could not explain inconsistencies. For instance, all elements were not in order according to atomic mass. In 1913, Henry Moseley explained the discrepancies. He discovered the correlation between the number of protons, atomic number, and frequency of X-rays generated. Entries today include atomic number and symbol and are arranged according to electron configuration. So when I was harping about this electron configuration being important, and it being all about the electron, this is why. When you think about the periodic table, it is one of the most instantaneously recognized symbols of, ooh, you are doing science, right? So as a science icon, it is hugely important. If we take our periodic table and we kind of stretch it out, right, we get something that looks like this. And what we can see is that we have arranged the periodic table based on those orbitals. So we have something called the S block over here on the left. Those are alkaline or alkalite earth metals. Over here on the P block, right, these are things that are starting to have elements that fill up P electrons, and things in the P subshell and the P orbitals. So remember, there are three of those. So 3, 1, 2, 3 times 2 is 6. And then over here you've got S's, and each S can hold 2. So it's 2 plus 6 is 8. This is where that rule of octaves is coming from, or that octet periodicity is coming from, the idea that you've got some S's and P's. You've got one S orbital, 3 P orbitals, each holds 2 electrons. 2 plus 6 is 8. Now, when we draw the periodic table, right, we've got this stuff in the middle. These are where you're starting to fill in those D shell electrons. And then you got the F block in here. Now, normally we don't draw this F block here just to save space. We cut it out and move it down underneath it, right? That's our lanthanides and our actinides. Right? Are there rules for filling this guy up? Yes, absolutely there are rules for filling that up. Looking at some of the elements essential to life, you got hydrogen and oxygen, right? That's water, right? You've got a protein, right? So proteins are made out of amino acids, so you're going to need some carbon, some nitrogen, some oxygen, right? Phosphorus is very important for life. Sodium, part of salt. What's really interesting is that when you talk about the solar fission fusion processes, stars are mostly hydrogen. But then when you look at the second most common nuclear process, it's something called the CNO chain. You start taking some of the helium and hydrogen, you start making carbon, and then nitrogen, and then oxygen. And these are some of the elements that we need the most, just happen to be the ones that are in that CNO chain. So this is what our modern periodic table looks like. Each spot on there is going to have its own unique electron configuration. That's what these numbers are in here, right? So 5s2, 5p2 is telling you what electrons are in what orbitals, right? So if I look at this periodic table, right, I know that if something is over here, its outermost electrons are going to be in an S orbital. If I look at something over here, its outermost electrons are going to be in a P orbital. If I look at something in here, its outermost electrons are going to be in a D orbital. And these guys are going to be in F orbitals. What makes this really powerful is that this 1, 2, 3, 4, 5 is also going to represent those N levels. So if I'm looking at N is equal to 1S, right? N is equal to 1S. Here we've got 2, 2S, right? 1, 2 in the 2 S's. And then over here is our 2 P's. We don't have any 1 P's, but we do have 2 P's. Right? So your periodic table is actually going to be used to kind of cheat and tell you what that electronic structure is. And these are just some fun representations of how can you represent that periodic table, right? So you can kind of take those lanthanides and fold them in on themselves, or you could arrange it kind of in a stack, like a Christmas tree, or you could do it as a racetrack, right? Or you could do it as modified racetrack, or you could do it as a stack, or you could do it as a pyramid, or you could do it as a clock, or you could do it as a spiral, or a disk, or a galaxy, or an actual, physical table, or you can organize it based on electron